A system's adiabatic constant, or heat capacity ratio gamma, is defined as the ratio of its heat capacity at constant pressure to its heat capacity at constant volume. Interestingly enough, we can measure this experimentally without heating up a system at all, using Ruchart's experiment. In this experiment, we have a chamber filled with some gas, sitting at some pressure P. And we have a piston sitting on top of that chamber, just being pushed down by its own weight plus atmospheric pressure. Now obviously, if atmospheric pressure plus the weight of the piston is equal to the pressure of the gas inside the chamber, this whole thing will be at equilibrium and the piston won't move at all. However, if one is greater than the other, we know there's going to be a net force on the piston and it will move. Now, while atmospheric pressure and the weight of the piston probably aren't going to change at all over the course of this experiment, the pressure inside the chamber is greatly affected by the volume, which is itself affected by how high the piston is. So we can write that down using the adiabatic gas relation. Pressure times volume to the gamma power equals some constant. And we can describe the force on the piston as just the net pressure times the area, which is of course equal to the mass of the piston times its acceleration. So we can use this equation to relate change in pressure to change in volume. And we can of course note that the change in volume is just the area times the change in x. We'll note that the net pressure is just the change in pressure based on how far the piston deviates from its equilibrium position. And so when we combine all these, using double dot shorthand for second derivative with respect to time. So if we substitute omega in for this, we get just a simple harmonic oscillator equation. That means if the piston deviates from equilibrium, it's just going to bounce up and down. And the frequency is going to depend on gamma. Once we solve for gamma, we get this expression. And we can measure all of these before we even do the experiment. And then gamma is just a function of the frequency squared. So we plug in these values. Note that the equilibrium pressure that we're measuring around is the atmospheric pressure plus the weight of the piston divided by its area. And plugging that all into our equation, we get gamma is 0.005 f squared, and that's in hertz. And here's the apparatus itself. It's a little air chamber with a piston that's rather airtight. In order to keep it oscillating smoothly, we'll actually be pumping in air in between the piston and the outer walls as an air bearing. And we'll also be continuously pumping pressure into the bottom chamber in order to keep the pressure consistent. Now we can measure the oscillations directly using this accelerometer that's on top of the piston. So we can read the feed and measure it directly using this oscilloscope. We'll start by looking at a diatomic gas. Since air is 99% two diatomic molecules, nitrogen and oxygen, we'll just try feeding that into here. Here we have a frequency of about 16.7 hertz, which corresponds to a gamma of 1.39 according to our equation. And that very closely matches the accepted gamma of 1.4 for a diatomic gas. Next, we're going to try a monatomic molecule, helium. Here we have a frequency of 17.8 hertz, corresponding to a gamma of 1.59. which very closely matches the accepted value of 1.6.